let's try to set up some of the problems that are on this sheet. All of them involve these two graphs that intersect at 2 points. Y is equal to e to the x minus 2, y is equal to 2x minus 1. Number 1 says, find the area of R. So find the area of this region. So the first thing I'm going to do is slice it. Let's see if I can make a slice right here. That slice is a rectangle. So the area of the rectangle is simply the height times the thickness. All right, the height of this rectangle is top minus bottom. So the top is the line, the bottom is the exponential. So that is the height. The thickness is going to be along the horizontal, so that'll be dx. That's the thickness. And I'm going to add them up from this x value right here to this x value. Those will be my bounds. And I wrote them on the board. This is the left bound, that's the right bound. I've clearly labeled them A and B, so I can just put A here and B here. Now I can say that is the area. All right, number 3, find the volume generated if this region, R, is revolved about the line y is equal to -2. So take this. I'm going to take a shot at drawing it a little bit. And if I draw it, good, fantastic. If I don't, no problem at all. It is no problem if I don't get it drawn real well. All I need to do is know what one slice is. So I got this volume. We can talk about what it looks like, whatever, it doesn't matter. Don't really care. What I want to do is just look at one slice. So I need to know what one slice looks like. So if I were to take this volume and took like a 2-bladed saw up here, double-bladed saw real close together, and cut a little portion out of it, what would it look like? Well, it'll look like this figure right here. In calculus circles, we call this a disk. So all I need to know now is what's the volume. This is a washer, I'm sorry. This is a disk cut out of a disk. So what is the volume of this washer? It is, let's see if I got room to put it in here. The volume of the washer is pi times the big radius from the center out here, whatever, the big radius squared times the thickness. So that is pi times big radius squared times the thickness minus the volume of the inside, which is also a disk. It is pi radius squared, but this time it's the small radius times the thickness. Okay, so now what is, I'll factor out the pi. What is the big radius? The big radius goes from the very outside to the center, from here to there, from here to there, from here to there. You could say it's from here to there. That's exactly right, but I don't have the formulas for those equations down here. So this is the top minus the bottom. So the top this time is going to be that line, 2x minus 1, minus -2. And you can, of course, put plus 2. I'm going to put minus -2. So this is pi times the big radius squared times the thickness. I'm going to factor out the thickness minus the small radius from here to there. From from here to there, from here to there. That is the exponential minus the center. And the thickness is dx. Thickness is dx. Okay? Now I can add all these up from the same places that I did this area. So that is from A to B. If I have A and B clearly labeled on my paper, I can use it over and over again. Okay? Now, number 8. Find the volume generated if R is revolved about the line y is equal to 5. All right, this bound here is a little bit less than 4, so 5 is out here somewhere. I'm going to take this region, this time revolve it about a vertical line. All right, so let's see what it looks like. Once again, I'm going to take a shot at drawing it. If I get a pretty good picture, fine. If I don't really care. Now, take a slice and want the slice be the same thing. Just like right here, this is like one slice in this picture. Well, here, slice this time, I'm going to have to slice it perpendicular to the y-axis. Okay? So the thickness is going to be a little different this time. So let's see what, if I can draw one slice. All right, I've got the same formula. It's actually the same cross section as before. So I can continue to look at this, and so it's going to be pi, the volume of the washer, pi, times the big radius squared. Now what is the big radius? The big radius this time goes from here to there, from here to there, from here to there, from here to there, which is 5 minus, and the big radius goes from the center all the way to the line this time, okay? But I got a little bit of a problem. I'm just gonna say line right here. 5 minus line squared, that's gonna be the big radius, minus, I'm factor out the pi, 5 minus, I'll say the curve, whatever, squared, times the thickness. All right, so factor out pi, what is the thickness this time? And we can see the thickness is not like it was here, dx, the thickness is dy. Well, that changes everything. So if I have dy here as a thickness, everything has got to be in terms of y. All right, so what is the line in terms of y? So we'll take the line, solve for x, and you can see that this is what we get here. So that's going to be 5 minus y plus 1 over 2, all squared. That's the big radius. Minus 5 minus the exponential this time. Here to there, from here to there, from here to there. So that will be 2 plus ln y. All that squared. And I need these brackets here. The pi's got to be multiplied by both of them. The dy has to be multiplied by both of them. All right, now how about the bounds this time? Will it go from A to B? No, the actual disc or the washers this time start down here and move up my page or my board here. So, and this is dy, so these bounds have to be in terms of y. So when I did the intersection on the calculator, I recorded the y intersections. And I wrote them C and D, so I'll just put C and D right there. As long as I got it clearly labeled on my paper. Okay? Now, number 9. Find the volume of the solid if R is the base and each cross section cut perpendicular to the x-axis is a square. Okay, so visualize, here is, I got this solid that's coming out of the board at me. And if I take it and like just cut it right here and separate it, visualize that. Then I cut it and separate it. If I stick my head here and look at the end of it, I'll see a square. Now look at this end of that solid, I'll see a square. Well, let's do something different this time. I'm gonna take a two-bladed saw with blades really close together and cut out a little section of that solid. Take it out, look at it. It'll be this. This is what we'll get, which is a rectangular solid. Now, all I need to know how to do, all I have to know how to do to get this hard calculus problem done is be able to find the volume of this thing. And I think a pretty smart fifth grader could do that. So I'll just call this a slab. Long story while I do that. But so what is the volume of this? I'm gonna say it's this dimension, I'll call it that the height. This dimension coming out this way, I'll call it the length. I could call these other things. This dimension here, I'm gonna call it the thickness. Okay, so let's see if we can figure these out. All right, so here it sits in here. So what is the height? That is from here to there. I'll draw 2 or 3 of them. Here's a real small one down here, perpendicular to the x-axis. Maybe get a little picture of what the solid looks like, doesn't matter. So the height is from here to there, which is the line, which is y is equal to 2x minus 1 minus the exponential, e to the x minus 2. All right, that is the height. What is the length? Well, this is a square. This face is a square, so this dimension is the same as that dimension. Our math forefathers and foremothers have given us a real cool way to write this thing right here times itself. That is this squared. And the thickness is dx, okay? I'm gonna add these up from here to there, which are my x values this time. So I'll just say from A to B, okay? Very good, very good. That is number 9. All right, let's try number 11. Number 11, find the volume of a solid if R is the base and each cross section cut perpendicular to the x-axis is a semicircle. So, same deal, everything's the same region R, but this time I'm gonna make a cut. If I just cut it right here, it's a solid coming out at me. If I cut it right here and open it up and looked in here, I'd see a semicircle. Look over here, I see a semicircle. Once again, like before, I'm gonna take that saw that I've actually never seen before, and I've seen a bunch of saws, that is 2 blades really close together, and just cut this solid and take a little piece out of it. And if I do that, it would be this. This is what it would look like. So, can we find the volume of this? Well, we can see that this is a circle with some thickness. We call that a disk, all right, which is the area of the base, which is pi times radius squared, times the thickness, but this is only half of that, so we got to bust it in half. So, let's see. The volume of that slab is going to be pi times the radius squared, but I need just half of that times the thickness. Okay? All right, so this is going to be, I'll say pi over 2 here. All right, what is the radius? Top minus bottom, top minus bottom. So that is the line, which is 2x minus 1 minus the exponential e to the x minus 2. Oh, wait a second. This is the diameter. So the radius is going to be half of that. And so it's going to be pi times the radius squared times the thickness over this 2. Take half of it. And the thickness is going to be, well, will it be dx or dy? Is it thick like this or is it thick like that? Well, we can see that it's thick, a horizontal thickness, which is going to be dx. So let's add these up. And these slices go from this x value to that x value. So I go back to my A and B. So that is the volume. All right, one little note about this. So often I've seen this problem in the multiple choice section of the AP test. And the way the answer is presented is in a little bit of a simplified manner. So let's see what would happen here if I put the constant on the outside. We'll put just pi over 2 on the outside. Well, how about this 2? Put it on the outside with that constant. So now it will be pi over 4. You can count on that being one of the answers. That's not correct. No, this is not 2. This is 2 squared. So we got pi over 2 here, 1/4 here. So what would be on the outside is pi over 8. Okay, fine. Let's look at one where we cut it perpendicular to the y-axis. Look at number 15. All right, find the volume of a solid R, or find the volume of the solid if R is a base and each cross-section cut perpendicular to the y-axis is a semicircle. So same problem, except the semicircles are lying in like this. This one's too big, it won't fit in there. So we've got that. All right, so same kind of formula here. Here's my same formula, but I gotta be a little careful here. What's true about my thickness? I can see that my thickness is gonna be dy this time. So let's see if we could go ahead and write the whole thing. So it's gonna be pi, and it's a semicircle, so pi over 2, and I can put that on the outside, you know that. All right, the radius, the diameter is gonna go from here to there. This is gonna be the diameter. The radius is gonna be half of that. So the thickness is gonna be dy. So once again, I had to take this and solve for x. All right, so, and I wanna have a positive number. I know I'm squaring it, won't matter, but I wanna be careful because it might bite you later if we're not careful. All right, so it's gonna be the curve, the exponential, this time it's actually a logarithmic equation or expression, that minus the linear. All right, this is the radius. No, that's the diameter, I'm sorry. That's the diameter. So I need to take this, bust it in half, square it, and the thickness is dy. So what are my bounds this time? My bounds will start down here and go up this way. So this is from C to D. Okay? Good.